Hello everyone. Let's start this lecture. So today we will talk about the isolated singularities of a holomorphic function and the so-called residue theorem. So first, let's define an important singularity of a holomorphic function. It's isolated. Singularity of a holomorphic function fz at z equals a means that fz is holomorphic on some deleted open disk neighborhood. Strictly less than z minus a absolute value, strictly less than capital R, where capital R is a partial number of point A in C. In other words, if you draw a picture, just punctured disk centered at A with radius R, capital R. That's why we call it isolated singularity. And first recall that last time we learned the Laurent series expansion of F on the degenerate open annulus. Zero less than z minus a absolute value less than capital R. In other words, you just take the small r to be 0 in the notation of last time. If you repeat the argument we did for the non-degenerate annulus last time, we will have the same conclusion that f can be written down as infinite sum from negative for n from negative infinity to positive infinity, Cn times z minus a to nth power, and moreover, it's absolutely and uniformly convergent on 0 less than R1 less than or equal to absolute value z minus a less than or equal to absolute value R2 less than R. In other words, you take the punctured disk and inscribe an annulus inside it. The annulus is a closed set. Then Fz, then the powers, and then the limit of the sequence of functions is Fz. And this convergence is uniform. In other words, you can interchange the order of summation on the right-hand side in arbitrary way. Okay, and Zn, just as what we did last time, can be computed in the following way. It's 1 over 2 pi I times the line integral along the circle of fz dz divided by z minus a to n plus 1's power for any small r between 0 and capital R and any n in z. Recall that last time we showed Cn actually is independent of the choice of small r. Okay, and then we define the part for n from negative infinity to negative 1, Cn times z minus a to n's power is called the principal part of the function f in this setting. Okay, next. This type of singularity, isolated singularities, exhibit a lot of interesting properties in complex analysis. Actually, if you only focus on the algebra geometry, then that's the only case you would have in dimension 1, in complex dimension 1. Okay, if you are interested in more weird functions, so I should say, if you are only interested in algebraic geometry, if you do the string theory or whatever, you might have, you will use this information. This is a very hot topic in mathematics as well. Then the worst singularity you would have is isolated singularities. Actually, later on we will introduce a special case, subfamily of isolated singularities called poles, and actually we will only have poles in number theory or whatever. You will only have those special functions. Okay, and but if you consider more general the complex world, complex analytic geometry, we are interested in complex analytic geometry. We definitely have worse singularities than isolated ones. Okay, but for our purpose, I will not get into the detail of the singularities worse than the isolated ones. As I said before, usually people study the most interesting topics. And if you want to study those interesting sub-objects, you usually put some good assumptions. Here, the good assumption is isolated singularity. And furthermore, the pose. Okay, now let's, in one dimension, actually we can classify the isolated singularities. So first type is called removable singularities. So from name, you can see those singularities can be removed. There's no singularity at all. So the definition is as follows. So remove singularity consists of the case of all the negative coefficient is zero, are zero. So gives a removable singularity. Which means that the function defined by the power series and from 0 to infinity Cn z minus a to nth power is a holomorphic function on the whole disk, which extends the given function fz. So here extends means, what does extends mean? Means fz equals gz if 0 less than norm z less than r strictly. So more intuitively, that means you can assign some value at a point number, for example delta, at the origin for f, so that f is holomorphic on the whole disk. So that's a precise definition for removable singularity. Okay, and from the definition, we can immediately draw the following proposition. If fz is bounded on some puncture disk or deleted neighborhood of A, the function fz has a removable singularity at z equals a. That is, fz can be extended to a holomorphic function on a neighborhood of z equals a. So we first prove this, and then I'll give you some remarks. So it suffices to prove that C negative 1, according to the definition, C negative 1, C negative 2 equals C negative n all the way up to infinity equals 0. Now, let's compute Cn. By definition, the absolute value of Cn is 1 over 2 pi I, the line integral along the disk of radius r, fz, z minus a to n plus 1's power, dz. Of course, this is less than 1 over 2 pi times supremum z minus a equals r, capital absolute value of f times 1 over r to n plus 1's power and dr. Sorry, you have r times 2 pi r. That's the length of the circle. Okay. And since f is bounded near point A, then if we take r small enough, then this term can be bounded by some constant, partial constant, capital M. Okay, then this one is less than or equal to m times r to 1 over r to n's power, which goes to 0 as r goes to infinity, goes to 0. So why this is true? For n is negative. Okay, but recall that Cn is independent of the choice of the radius r. This is by the Cauchy-Coushac theorem. Then Cn must be 0 for n from -1, -2 all the way up to -infinity. And then by definition, we know f has a removable singularity at point A. Okay, so let's make several remarks. Firstly, it is easy to see the inverse direction is trivial. That is, if fz is holomorphic on the whole disk, then fz must be bounded on the puncture disk. This is because f is continuous if it's holomorphic. And the remark 2, so this proposition actually is called Riemann's removable singularity theorem. It has a higher dimension generalization. I will not get into the details, but basically, you noted that, well, I can list the properties in the following. Firstly, if f is bounded near singularities, in higher dimension, the singularities might not be isolated. Then f is holomorphic. Or f extends into the singularity. The singularity just fake singularities. It's removable. But actually, I didn't tell you what is holomorphic function in higher dimensions. But basically, probably you can think of it's several complex variables. It's very easy to define. F z1, z2, which is a power series expansion. Z1 and Z2, so you have double sum. Okay, I will not get into the details. Secondly, if singularities, the set of singularities is of codimension, complex codimension, at least 2, then f extends into singularities holomorphically. Here it should be holomorphically. Notice that in one-dimensional case, the codimension cannot be at least 2 because totally you only have one dimension. Okay. In higher dimension, this phenomenon is new. You can extend without any assumption on the boundedness. And thirdly, so here you see you have boundedness. Actually, this boundedness is pointwise bound. But if you know a little bit Math 522, then you know instead of pointwise bound, you might have some other norm, just like L2 norm, LP norm. So if f is L2 integrable. On the puncture disk, then F is holomorphic in the whole disk. This is very hard, actually, but you can prove it. Probably later on, if we have time, at the end of this course, I will show you how to prove this. And the consequence of this is famous Uhlenbeck Sachs theorem. Okay, which shows that harmonic maps under certain conditions has no singularities at all. Okay, I will, as well, I will not get into the detail of this huge story. But you can try to formulate these three things, try to understand the statement, or search online. Those are very fundamental theorems in algebra geometry, in differential geometry, of course in several complex variables, but their roots are the Riemann's removable singularity theorem, just this simple theorem. Okay, next we will define the second type singularity. Actually, this is the most important one. In the future for you to study in the later courses. So let's first give the definition. The singularities at z equals a is a pole if Cn is 0 for n less than negative k and C negative k different from 0, where k is a positive integer. And then the number k is called the order of the pole of Fz at z equals a. Proposition 1, Fz has a pole at z equals a if and only if limit absolute value of z of Fz when z goes to a is infinity. I will first give the proof and then I will give some remarks about the significance of this theorem. Actually, this type of theory is just a most simple case of the so-called value distribution. Okay. So suppose Cn is 0 for, we first prove this direction. Then we have the following statement. Cn is 0 for n less than negative k and C negative k is non-zero, where k is some positive integer. And since fz then can be written down as fz divided by z minus a times k, where g is a holomorphic function with a power series expansion. And the leading coefficient, c negative k, is different from 0. Or in other words, the value of g is non-vanishing at point A. So because of this fact, it follows that the limit of the absolute value of f when z goes to A is, you plug in, is the limit of the quotient, and notice that when you choose z close enough to A, the gz is bounded below by the norm of gz is bounded below by the half of the norm ga. Okay, then this is a constant, non-zero. So if you take a limit, it's positive infinity because this blows up. Okay, next, let's prove the other direction. On the other hand, suppose limit absolute value fz when z goes to A is infinite, then there exists some positive number r0 less than r, such that fz at least 1 for the smaller puncture disk. Now the trick is consider the reciprocal of the function f. On the puncture disk, then the holomorphic function hz is bounded by 1 from above, bounded by 1 in absolute value. On the puncture disk, hence, by the removable singularity theorem, it is removable. Hence, the point A, point 0 is a removable. It's better to say the origin, since hence the origin is a removable singularity. Holomorphic function h Moreover, we can write Hz as a power series expansion. Recall that we assume the limit of fzn is infinity when z goes to a. Oh, my bad notation here. The fixed point is a. We consider disk centered at A. Okay. Okay. Since the limit of absolute value of f at A is infinity, it follows that limit h when z goes to A is 0. And then by previous study, we know that, and hence hz can be written down as z minus a to k's power times, let's call this function gz, where k is a positive integer such that g a is different from 0. Or equivalently, we have dk is different from 0 and dn is 0 for n between 0 and k. Okay, now let qz, no, now from the definition we can compute gz. Gz just summation n from 0 to infinity dn plus k z minus a to n's power. Which is, of course, holomorphic on the whole disk z minus a less than r0. Since gz is holomorphic, and ga is different from 0, then there exists a smaller disk z minus a whose value less than r1, less than R0, such that 1 over QZ is holomorphic on Z minus A absolute less than R1. Then Fz equals 1 over Hz is 1 over Z minus A to k's power times Gz. Oh, here's G. Sorry. Equals 1 over Z minus A times K times 1 over Gz. So since 1 over Gz is holomorphic, then you can do a power series expansion in the small disk with coefficient En. Okay, and then so here for Z minus A less than R1, then we can conclude that by the uniqueness of the coefficient of a Laurent series expansion, as we mentioned before, how to prove the uniqueness, we can apply the Cauchy-Goussat theorem to derive this expansion. It follows that Cn is En plus k, which is 0 for n less than negative k, and Ck is different, C negative k, C negative k is different from 0. So that's the other direction. Okay, and then we have proposition 2. So actually it's clear from the proof that this k kind of characterize the blow-up order. So this observation is explicitly stated in the following proposition: the order of a pole is an integer k such that limit z minus a k's power fz is a positive number, which is neither zero nor infinity. So prove let fz. So now we know f is a pole. F has a pole at A, then we can write in this way with C negative k prime different from 0. K prime is a positive integer. Then let's compute the power series expansion for the holomorphic function, for the function z minus a to k's power times fz. So this is, you do the product, you factor out z minus a to k prime's power. Okay, then this is z minus a k prime k minus k prime times summation of power series. And for the power series, note that the leading coefficient is non-zero. Okay, then if k prime less than k, then, so let's call this green part, this blue part. Green part. Green part is bounded. Blue part goes to 0. Hence, the limit is 0. And if k prime greater than k, then green part has the argument as before. Green part is bounded from below by a positive constant. Blue part goes to infinity. Then, hence, limit f z minus a to k's power f z is infinity. And lastly, if two parameters are the same, then limit z minus a to k's power times fz absolute value is limit absolute value of the green part subpower series which is c negative k prime, which is absolute value of this. Of course, by the assumption this is strictly larger than 0. So we are done. So I will write down the remark for this one. The order of pole characterize the growth of the function f near the pole. And the remark 2, so here you see we have we related two different properties together. On this side, on one side, you have the algebraic information, the order of pole. From the proof or from the definition, you know it's an integer, and it has very elementary algebraic properties. Okay, on the other side, you have the analytic information, growth of function f. And later on, people generalize this kind of properties to various settings. So probably we don't have time to talk about Jensen's theorem, but they are very important in number theorem and value distribution, and then Navelina theorem, which share the same principle here. They also relate the order of pole, but now probably your function has poles, has zeros, how to group them together. And then on the other hand, you have the growth of function, analytic property of the function, maximum value of the function on the circle. Yeah, so if you have interest, you can look up this. And remark 3, for the proposition 1, actually you see near a singularity, you cannot prescribe arbitrary value. So we have value distribution theorem associated with singularity. As we met, probably, I don't know if you still remember, probably we mentioned before that we have Picard's theorem, which showed that near singularity you can only miss at most 3 points. And it's also, this theorem is also included in Navelina's theorem, which is called second fundamental theorem or first fundamental theorem. Okay, so last remark. The concept of pole can be generalized to higher dimensions. The concept of poles. Generalized high dimension means a function involving more than one complex variables. So you can think about how to generalize it. Later on, when we define, just in a moment, when we define meromorphic functions, I will tell you. Okay, next. we studied the essential, the third type of singularities, which is called essential singularity. And you will see from the definition of essential singularity, actually this just include all the remaining cases for an isolated singularities. Because for isolated singularities, you have Laurent series expansion, and you can write down as power series from negative infinity to positive infinity. And for the coefficient, you can only have three possibilities for the non-vanishing coefficients with the least index k, then either k doesn't exist, or k is a negative number, or k is positive number, or k is a non-negative number. That corresponding to essential singularities, poles, and removable singularities. Okay, so let's give the definition. The isolated singularity z equals a of fz is called an essential singularity if Cn is different from 0 for an infinite number of negative integers m. And we have the following proposition. Just as before, we want to characterize the essential singularities by the distribution of the function values near the singularity. So this is a theorem due to Casarati and Weierstrass. Z equals A is an essential singularity of Fz if and only if for any zero less than R less than capital R, the image of the small puncture disk and the map Z goes to Fz is dense in C. So I would like to draw a picture. So that picture means that if you have essential singularities, then you cannot predict any information from the essential singularity. That means no matter which how small the disk subdisk you choose, when you map it to the domain C, it gives you dense set. And the same thing for A. Okay, actually, here is puncture disk, and the puncture disk inside as well. So that's a geometric understanding of the theorem. Now let's make a remark. Recall that a set E is dense in the complex plane is equivalent means that any non-empty open subset OC contains some point of the image. Okay, now let's prove the theorem. We first do this direction. We want to conclude the essential part based on the assumption the image of any subpuncture disk is dense in C. So if Z equals A is removable, to prove that we just exclude the other two possibilities. Then FA can be defined because it's a removable singularity to make FZ is holomorphic on the disk of radius R. Here Z minus A, and hence there exists some positive number small r less than capital R, such that because F is holomorphic, hence it's continuous, we can take such R such that the absolute value of Fz is bounded by absolute value of Fa plus 1 for any Z minus A between 0 and R. And then, therefore, the image of this special puncture disk and F cannot be dense in C. If you draw a picture, it's clear because now your image is bounded in the disk or centered at 0 with radius absolute value of Fa plus 1. So no matter how well your image is, by this estimate, it's contained in this ball. Then it contradicts the assumption the blue set should be dense in C because you have some outside part. For this point, for example, you can take a small pole such that there's no blue points. Okay, now let's prove the other direction. So we want to show that if this is essential, then it must be, oh sorry, my bad, we still need to exclude the pole case. So if z equals a is a pole, then limit z goes to a f z is infinity, and hence there exists some. So the argument is similar to the above case. It exists a small disk such that absolute value of fz is greater than 1 for 0 less than z minus a absolute value less than r, and hence the image of the disk 0 less than z minus r less than r, and f is not dense in C. If you draw a picture, what does that mean? Oh, sorry, I should use, for consistency, I should use yellow color. So now you draw a disk with radius 1, and then your blue part, no matter how weird it is, it must be outside the red disk. Then if you take a point, for example at the origin, then with a small ball, then in this small ball there's no red point. So so the idea, don't try to remember the proof, try to understand it. The proofs just distinguish the value distribution for a pole and the removable singularity from the essential singularity. The essential singularity, you cannot find any pattern except the kind of egoticity or just equal distribution. If you know a little bit physics, it's just equilibrium. You don't know any different part of the singularity. But for pole and removable singularity, you do have some different properties. One is function is bounded, the other one function grows very fast. So that's kind of distinguish them from the essential singularity. And for the proof, we just use this property. Okay, and lastly, we want to show the other direction from the essential singularity to dense in C. And we prove by contradiction. Assume there exists a small punctured disk whose image and f is not dense. In C. Now we want to reinterpret the dense property in the other way. Since it's not dense, then we can take open set U defined by the ball with radius r centered at B, radius rho centered at B, intersect the image of the small disk, which is empty, where rho is positive. Let's understand this. Try to understand this statement. Because now the blue part, the image. So this is the image. Okay, if you map to this complex plane, then you have some distribution of the green points. But then since it's not dense, then you can find a point B with a small neighborhood rho, with radius rho, such that in this open set, there's no blue points. So that's exactly the meaning of this. Okay, now from this you already have some boundedness property, and it's not equilibrium. So the technique is, if you consider the function g, which is defined by 1 over f minus b, of course it's not holomorphic on the whole complex plane, but on the puncture small disk, z less than z minus a less than r, this is holomorphic. And moreover, noted that gz absolute value is 1 over fz minus b absolute value, and less than 1 over rho for z minus a less than r, less than 0, less than r. Then G has removable singularity at z equals a. Since G is not identically 0 on z minus a less than r, Gz, we can factor out z minus a where k greater than 0, ha is different from 0. Then fz can be solved by this 1 over z minus a to k's power hz. Then then a is not an essential singularity of f. We're done. Okay, so as I mentioned before, I make a remark here. The value distribution for essential singularity exhibits kind of equilibrium. phenomena. Okay, I will stop here. Next time we will talk about the most interesting part of the singularity theorem, that is the pole, and we want to introduce the residue of any function with pole singularities only.